Okay, so this is a work function problem. So our formula for that is that the maximum kinetic energy of the escaping electrons is equal to the energy of the incident light minus the work function. All right? Now let's find the energy of the incident light first. That's going to be hc over lambda. Okay, so kind of write out all these constants over, and the wavelength is 378 nanometers. Okay, so that's 5.26 times 10 to the minus 19 joules, or 3.29 eV. We got to be careful here to make sure we get everything in the same units. Now the kinetic energy, the maximum kinetic energy, since it gives us the maximum speed that electrons escape the metal, that tells us that that's the maximum kinetic energy. Okay, so that's 1/2. Now these electrons have a mass of 911 times 10 to the minus 31, and the speed is 7.2 times 10 to the 5th. I square that. So that gives me 2.36 times 10 to the minus 19 joules, which is 1.48 eV. Okay? So, now I'm good to go. I can take this equation here, and I can say that the maximum kinetic energy is equal to the incident energy minus the work function. Notice that I got both of these numbers here in eV. You don't want to mix up eV with joules. It doesn't work, and it'll give you a nonsense answer. So phi, the work function, is 1.81 eV. Now for part B, that's part A, it says what's the maximum possible wavelength of light that may illuminate the metal and still allow the electrons to escape? So they're asking for the cutoff wavelength, right? Another way of asking that is what's the minimum energy that can illuminate the metal and still allow the electrons to escape? Well, at minimum photon energy, the maximum kinetic energy of the escaping electrons is basically zero. It's like 0.000001. So they basically have no energy left over, which means that the energy of the incident photons is just equal to the work function. All right, you've got barely enough energy to get the electrons out of the metal, and they don't have anything left over. So all I got to do is set hc over lambda equal to the work function, or lambda is equal to hc over the work function. But I got to make sure that all this is in MKS units. The work function is going to be in joules for this to work. So lambda is 6.626. So there's Planck's constant. There's the speed of light. And I'm going to divide by the work function. Now the work function is 1.81 eV. That is, well, I can just do the conversion down here. 1.81 eV multiplied by the conversion factor, 1.6 times 10 to the minus 19 joules per eV. Okay, now if you calculate all that out, you get 6.86 times 10 to the minus 7 meters, which is 686 nanometers.